Now we'll speak about notations and definitions. So let's first start with data structures. There are different types of data. Firstly, there are scalars, which are simple numerical values: 15, minus 3.25, 0.7, just one single number. Any variables that will have a scalar value will be denoted in this book with an italic letter, italic font, where the letters are more cursive and slightly tilted. So like X here and A are examples. A vector is an ordered list of numerical or scalar values, and each scalar value in a vector is called an attribute. Any scalar value in this book will be denoted by a bold font, like when your alphabet. So for example, we have a vector A here, which has the attributes 2 and 3, B here, which has attributes minus 2 and 5, and C here, which has attributes 1 and 0. These attributes are given here. So in this case, as you can see, this is the location of the points. So in our case, A equals 2 comma 3, so A must be this red dot, since it is placed at x1, which is the first coordinate of 2, and x2 of 3, and our values are 2 and 3. So this must be our A, and this green dot must be our C, and that blue dot must be our B. So if we have a vector, and this power or this index, it's known as an index actually. So if we have this raised to value, for example A raised to 1, right, this simply means A index 1. So that means the first attribute, which in the case of A is 2. The second attribute, so if you have A raised to 2, will be 3. For B, the first attribute will be minus 2, and so on. The notation of a index should not be confused with the power operator, right? If you want to apply a power, like if you want to say square to an indexed attribute, so if you only want to apply a power to A raised to 1, so what you will do is you will put A raised to 1 and then put that whole thing in brackets, rounded brackets, and then after that we will put the power. A variable can have 2 or more indices. So for example, x in our case is the feature vector. I means simply the which feature vector are we talking about. So if we have number of bedrooms as the first vector, number of bathrooms as the second value, etc. So this is which x variable we are talking about, and then j is which attribute of that x variable are we talking about. So for example, in neural networks we denote it as x with L, U and J, right? Input feature is J, unit is U, and our layer number will be L. We'll go into that later, so let's not focus or worry too much about that. A matrix is a rectangular array of numbers arranged in rows and columns. So simply a matrix is when you have numbers, structured in a tabular form, rows and columns. Like here you can see there are three columns and 2 rows, right? Matrices are denoted with bold capital letters. So vectors are denoted by bold lowercase letters, and matrices are denoted by bold capital letters. A set is an unordered collection of elements. So while a vector is an ordered list of scalar values, a set is an unordered collection of unique elements. So it's not necessarily that all the elements be similar, right? It could be 1, 3, A, B. It could then have a name like Jack, right? So it's not, while a vector can only have numbers as attributes, a set could have anything. It could have letters, strings, numbers, float values like this. A special set denoted R includes all numbers from minus infinity to plus infinity. So whenever you see this different type of R, it means that we are referring to all possible numbers. So simply when an element X belongs to a set S, we write it so. So this sign here uh, is simply told to say which. So this sign here simply says element X belongs to set S. We can obtain a new set. So and then there is this intersection sign, which simply means S3 is the result of the intersection between two sets S1 and S2. So simply all records which are common in S1 and S2 make up S3. So for example, we have S1 to be 1358 and S2 to be 184. If you will observe, you will see that S1 and S2 have two common attributes, 1 and 8. Both have 1 and 8 present. So our S3 will be 1, 8. We can obtain a new set S3 as a union of two sets as well. It will simply, so in this case we will use the opposite symbol of intersection. So while this was more like a lowercase n, here we have something like a U-shaped sign. So for example, if you have 1358 and 184, it will take all the unique values. So 1, 3, 5, so it has 1, 3, 4, 5 and 8, because these are all the unique values. It won't take 8 twice or 1 twice, because it has already written it down. So only unique values, and this is our new set which will be stored into S3. Now this is called, this sign here which looks like a capital E, though it's a bit different, is a sigma notation. So what a sigma notation does is, it simply asks you to sum a collection or the attributes of a vector. So whenever you see sigma, it means it's saying add up all of the following. So for in this example, you can see sigma, which is simply summation of this variable xi, where I equals 1. So what this means is, when I equals 1, we want x1, then if I equals 2, then add x2. So for different values of I, you are adding up different elements, and you will add up x1, x2, x3, x4 all the way to xn, whichever the final value is. The notation here, you can see it's DEF written over the equals to sign, is simply means defined as. So sigma of I equals 1, where your upper limit is n in relation to x of I, is defined as x1 plus x. So it's simply x, all the possible values of x added. Then there's something like a capital pi notation. So it is simply, while sigma notation was the addition of some products, this is the multiplication, right? It's the product of some elements. So here you multiply. Same rule applies. I equals 1 for different values of I, your x changes. So it's x1, then I becomes 2, so x becomes 2, then your I becomes 3, so x becomes 3, until I becomes n, which is your upper limit. And so you will just multiply them all to each other. We can also obviously omit this dot, this multiplication sign, because x1, because when you, for example, a dot b simply means a multiplied by b, but we can just omit the dot and simplify it to ab, because that also means a multiplied by b. Now there are some operations on sets, right? For example, you can say s dash equals x squared of x. So we are simply saying, we want, first of all, we want all the x elements which are present in set S. Actually, we will read this backwards. Okay, so rather than going from the left to right, you will go from right to left. So here you can see it's saying x is simply all numbers which are below 3. So 2, 1 and 0, in case there are no negative numbers. So it's saying 2, 1 and 0, if they are present in set S, then we want their squared values. So for example, our set S has 2 but does not have 1, and it does not have 0 either. So x values smaller than 3, which are 0, 1 and 2, whether it is present in set S, so we have only 2 present, square it. So our S dash will be equal to 4, because it squared the number 2, and this will end up with us creating this new set S dash. There is a this you can see this two stand asterisks or sticks sort of thing. This is a cardinality operator. It will simply return the number of elements in set S. So for example, in our example over here, where did it go? Yeah, here. In this set, S3 which we made, which had these values 1, 3, 4, 5, 8, if we use a cardinality operator, we added 2 asterisks, we would get 5 as the result because it has 5 elements in it. Now there are some operations you can run on vectors. Okay, you can add up two vectors x and z, and it is defined as the addition of the vectors individual elements. So x1 plus z1, so first element of x plus first element of z plus second second element of x plus second element of z. The result will also be a vector, but it will have the added value. So in this case, if you had a vector x which had the values 1, 2, 3, 4 and z which had the values 5, 6, 7, 8, so x1 plus z1 will be 1 plus 5, x2 plus z2 will be 2 plus 6, x3 plus z3 will be 3 plus 7, and so on. And the result will be a vector which will have values like 5, 7, 9, etc. The difference of two vectors, simply x minus z, is also defined like the sum. So, but it's simply like you replace the positive sign with the subtracting sign. So x1 minus z1, element 2 of x minus element 2 of z, and so on until element m of x minus element m of z. A vector if multiplied by a scalar. So simply if you have a vector 1, 2, 3, 4 and you are trying to multiply it by a vector by a scalar which is simply one value 3, what will be the result? The result will be you will take the one value, you will take the scalar and multiply it with all attributes of x, which is your vector. So you will take your scalar value and multiply it by all attributes of your vector. So in our case 1 into 3, which will be 3. The second attribute where our x is 2, so it's 2 into our scalar, which is 3 again, so 6, and then it will be 3 into 3, which is 9, and so on. A dot product of two vectors is a scalar. So what is a dot product? For example, you have two vectors w and x. So wx is defined by sum of all, so it's simply the sum of all the w, it's simply the sum of all w into w and x, right? Sorry, the sum of w into x multiplied by, right? So the dot product is denoted, so simply it says add up all the attributes of w into attributes of, first take all the attributes of w into all the attributes of x and then add them up. But for this the two vectors must be of the same dimensionality. So if your x variable has only 5 5 attributes and your w variable has 7, you cannot compute a dot product because the dimensions should be the same. The multiplication of a matrix W, so we are now getting to matrices which are represented like this. So here 1 is your row number, the first value is always your row number and your second value is your column number. So row number is denoted by I, column number is denoted by J. So this is row 1, so this first record here is row 1 column 1, second one is row 1 column 2, third one is row 1 column 3, and so on. So the multiplication of a matrix W by a vector X results in another vector. So for example, this is our matrix and we have a vector, but first of all the dimensionality has to be same, by which I mean we can only multiply a matrix by a vector if the vector has the same number of rows as the number of columns in the matrix. So our matrix has 3 columns, so our vector needs to have 3 attributes, right? Or yeah, so in our case we have x1, x2, x3, and this is, so what we will do is we will say okay, we can multiply this as the number of columns in our matrix are 3 and the number of attributes or the number of rows in our vector are also 3. So the result becomes w1 1 into x1, w1 of 1 comma 2 into x2. So we will take we will first take all the values in the first row, right, and multiply them with the, wait a second, what I mean to say is we will take all the values in the first row of our matrix and multiply them by the vector. Then we'll take all the values in the second matrix and multiply them by the vector. So we have the w11 multiplied by x of 1, w1 comma 2 multiplied by x of 2, w1 comma 3 multiplied by x of 3. Then you do the same for the next row, right? And then you add them up. So you add up the result of the first row multiplied by your vector, and then you add up the result of the second row multiplied by your vector. So you will have w of the first row multiplied by all attributes of vector x, and your values in the second row of the matrix multiplied by all attributes in vector x. The multiplication of a vector by a matrix is given by this T sign. So we can only multiply a vector by a matrix if the vector has the same number of dimensions as the number of rows in the matrix. So for example, in this case, our x has 2. We have 2 attributes in our matrix and we have 3 columns, but that will still not be an issue because we can use row numbers. So we will say, okay, x1 of 1 into w1 of 1 into x1 plus w2 of 1 into x2. So we are now simply multiplying column wise, right? But the vector x should have either have the same number of attributes as the rows in the matrix or the columns. If for example our vector has 2 attributes and our matrix is 3 by 2, we can use it, right? Because our matrix has two columns. But if our matrix is something like 5 by 5, 5 rows and 5 columns, and our vector is has only 3 attributes, you cannot multiply, right? Because who will you multiply the remaining values to? You have no number left. What is a function? A function is a relation that associates each element. So simply what it's saying is, function is when you are applying some equation, some formula on a variable x. So function, so y equals f of x. So for example, our target variable is equals to our f, which will be a statistical model when it is given the data x. We say our f of x, our function of x, has a local minimum at x equals c if our function of x is greater than our function of c for every x in some. So simply, what is a local minimum? So we will define an interval. Okay, in our case it's 0.2. So we will check and we will see what is the average value for our f of x in every interval, right? Then we will add these values and get an average. So for example, the average value is, let's say, 0. So we will see and we will say, okay, at x equals 1, our f of x is at a local minimum because it is below 0, which is the average of our function. A global minimum is simply the minimum value amongst all the local minimums. So this, at x equals 0.3, we also have a local minimum, and at x equals 1 we also have a local minimum. But our x equals 0.3, at x equals 0.3, our f of x is really low. It's like at -3, which is the lowest local minimum. Our other local minimum is at -1. So -3 is smaller than -1. So this becomes the global minimum. It is the smallest local minimum in the whole function of x. Next we have max and argmax. For a set of values where we have, for example, our a, which has values a1, a2, a3 to an, the operator max will return the highest value of our function for all elements in set a. So it won't return the highest value of a, it will return the highest value for our function. So in this case, in this chart over here, the highest value is 6 because we are talking about f of x. On the other hand, the operator argmax will return the element of the set A which has the maximum value of the function. So if we say we want max of f of x in this example, we will get 6 because that's the maximum value of f of x. If we say argmax, it will check, okay, at which value of x did we have the highest value for f of x. So 6 was observed at dot 1, so it will take that.